Hi everyone, myself Dr. Balu. Currently I am working as an assistant professor in the Department of Electrical Engineering. So this semester I am teaching the power system 1 to the B.Tech second year second semester students. So in the module 3, as I said in the syllabus description, so there I told that the module 1, module 2, module 3, module 4, the entire power system 1 is divided into 4 modules. So we'll discuss here the module 3. The module 3 will cover the load flow or power flow analysis. So first we'll see the modeling and representation of the power system components. Then we'll move forward to the remaining topics. So these are the books, reference books, which are used for discussing all the load flow analysis and the entire power system 1. And especially I will follow my book. So my book is published in the Kanna publisher. I myself and my guide Dr. Vivekananda Mukherjee, we wrote this entire book. So first we'll start with the representation of the power system components. So the basic components of the power systems are generators, transformers, transmission lines, and loads. And the interconnection among these components in the power system might be shown in the single line diagram or the one line diagrams. So we will see how the generators, transformers, transmission line, and loads we are connected in terms of the interconnected system or the radial system, that we will see in the single line diagram or one line diagram. For analysis of the power system, the equivalent circuit of the components are shown in the form of reactances or impedance diagram. So we will consider whether we'll show in the reactance diagram or we'll show in the impedance diagrams. So as for the IEEE standards and the American National Standards, ANSYS has published a set of standard symbols for the electrical circuit diagrams. So these symbols which will use to represent the single line diagram or the one line diagram. So first we will see here the 3-phase 3-wire delta connection and 3-phase 3-wire unneutral grounded. You can see the neutral ungrounded. Then we'll see the star connection with neutral grounded. Under this we will see the three different configurations. The neutral is grounded, the solidly, and neutral is grounded with the reactance, neutral is grounded with the resistance. Then we'll see the two winding transformer. We can show the two winding transformer with the step up and step down by using these two symbols. Then we'll see the circle which will represent the rotating machines in the power system representations. Then we'll see the current transformers, potential transformers, fuse, circuit breakers, air circuit breakers. Then we'll see the relays and the load. Okay, sometime in the power system which we'll see in the cross mark will represent the protective relays in the power system. So this is the simple single line diagram of the given electrical power systems. The each component is represented by using their symbol as per the IEEE and ANSYS. Okay, here this will indicate the generators. These are the circuit breakers, transformers, transmission lines, transformers, and the generators, and their corresponding generators how the neutral is grounded. And we'll see the load with the connecting with the circuit breakers. So we'll see what is the advantage of the one line or single line diagram. The advantage of single line diagram representation is simplicity. First we'll see the complexity we will remove by representing in terms of their equivalent circuit. So further we'll go for the symbol as for the IEEE and the ANSYS, and one phase representations of the all three phases. Under balance condition, no need to represent for the all the three phases. So we need to go for the by representing the single phase which will represent the three phases. And the equivalent circuit of the components are replaced by their standard symbols, and the completion of the circuit through the neutral is omitted. This is the very important. So when you go for the circuit representations, the written path we have to show the written path. So when you go for the single line diagram representations, so no need to represent the neutral throughout the circuit. So here we can show that directly confusion with the neutral we can omit it. Then we'll see the impedance and reactant diagram representations. When the symbols are given, then how we are going to represent their impedance of the reactant diagrams in terms of the equivalent of the transformer, equivalent circuit of the generator, equivalent circuit of the transformer, equivalent circuit of the transmission line. So this is the given simple power system network which are used to connect it by using the symbols. So first we will see the equivalent circuit of the generator 1, generator 2, generator 2, and generator 3. Then we will see the transformer 1, transformer 2, transmission line, and how they are connected in the delta star and the delta star delta manner. Okay, step up and step down. So here we'll see here this is the equivalent circuit of generator 1, equivalent circuit of generator 2, and you'll see the equivalent circuit of generator 3. So the voltage source in series with the impedance will represent the generator equivalent circuit. You can say the generator 1, you can say the generator 2, you can say the generator 3. Then we will see the equivalent circuit of the load 1 and the equivalent circuit of the transformer 1. This is the equivalent circuit of the transmission line and the equivalent circuit of the transformer 2. And you'll see the equivalent circuit of the load. This is the equivalent circuit of the load 2. This is the transformer 2. And this is the transmission line, this is the transformer 1, and this is the equivalent circuit of the load 1. So after this we will see the simplification of the given per phase impedance diagram for the load flow analysis. So here we can consider here the shunt elements of the transformer, the shunt element of the transmission line, and shunt elements of the, you can see the transmission line and the shunt element of the transformer 1 and 2 we can neglect when we are going to calculate the load flow analysis, or when you're going to consider the short circuit fault analysis. We need to ignore the shunt components, okay, shunt parameters of the transmission line and the transformer. Then we will consider here the only transfer reactance. So these are the only transfer reactance which will consider to form the equivalent reactance of impedance diagram of the given components. So generators, transformers, transmission line, and the load. And which will see here, this is the generator 1, generator 2, and transformer 1 transfer reactance, and the transmission line and the transfer reactance of the transmission line will consider here, and the reactance series reactance of the transformer will consider, and this is the generator 3. So this is the simplified impedance of the reactance diagram of the given power system, which was shown in the figure. We can share the figure 1, and this is the figure 2 is the equivalent reactance or impedance diagram of the given figure 1. Then we'll see the different components, then their equivalent circuits, or you can say the reactance diagram of the corresponding given parameter, given components in the power system. First we will see the synchronous generator. So synchronous generator, which can represent here the voltage source with the series reactance. So we can go here the mod E at an angle of delta, so which will represent the voltage source at an angle of phase angle of synchronous generator. Then we'll go for the transformer. Transformer step up, step down, whether it is connected in star to star, or delta to star, or delta to star to delta. So we'll always take in the per unit representation is the series reactance. Then the transmission line, again we'll see the series reactance in the per unit. Then we'll go for the synchronous motor, which will indicate here the, here you can go for the mod E at an angle of minus delta, which will indicate the synchronous generator. So in place of here you can write the delta. Then we'll go for the induction motor. So induction motor equivalent circuit we have seen in the per unit representation, series reactance in series with the resistance. And you'll see the infinity bus. This is the very important concept in the power system, which will see the why we are using the concept of infinity bus. So the simple concept is the bus voltage of the bus voltage is always 1 per unit at an angle of delta. That bus will represent in the power system is the infinity bus. Then we'll see the per unit representation of the per unit representation, to which we have to calculate all the values in the common base or given base. Okay, the power system lines are operated at the kilovolts level with the, we can represent in terms of the kV, and the most convenient unit to express the voltage. So okay, we can represent in the kilovolts or kilovolts. So most common way to represent the voltage level in the power system is the kV, that is kilovolts. And similarly we can see the power, the kilowatts or the kilovolt amperes. So if it is kilowatts, megawatts, kilovolt amperes or megavolt amperes, we can represent it with the real power and the complex power by considering the reactive power also. However, other quantities also there, we can represent it in the amperes and ohms. So each are expressed in there in the percentage or per unit of the base or reference value which you are specified. So for example, if we give the different values, so we need to compare the different parameters on the given values. So we no need to go for the kilovolts, megavolts, amperes, and ohms. So we need to convert all the values in the dimensionless, and we'll compare the performance. Then we will get the exact how the parameters is behaving on the common base. So what is the definition of per unit here? The per unit quantity, which will give the actual quantity, actual value of the quantity divided by base value of the quantity. So it will give the per unit quantity. Then the ratio in the per unit we can express as a percentage. So whatever the per unit value is gained, just to multiply with the 100, you will get the percentage value. Then if you go for the given value in the percentage, just to divided by the 100, you will get the per unit value. Then we'll discuss the most advantage or the major advantage of the per unit representation in the power system is, first we will see the transformer simplifications. So this is the very important, where we can represent the primary impedance and the secondary impedance in the per unit of transformer, both are same. So in the transformer simplifications, we can have the same impedance, easy comparisons, voltage levels, different voltage levels we can remove, and the simple network analysis. We can go for the simple common base. We'll choose one common base and we'll do the analysis. Okay. Then we'll see here how the base values you're going to choose. So these are the mathematical expression which will represent in the impedance in per unit in the single phase, impedance in per unit for the three phase. Okay, so we'll start with the single phase and the three phase. At the conclusion, we'll see that the per unit impedance in the single phase is equal to per unit impedance in the three phase. Okay, we will go and select in the per unit impedance in the single phase as the per unit in the three phase, both are same under the balance condition. Then we see the change of base of the per unit quantity. So the per unit value is given in the one base. I need to see that the per unit value on the another different base value. Then how we are going to change the bases of different quantities. So this is the simple formula which we have derived. That is per unit impedance is equal to actual impedance into MVS base divided by KV base square. So from here you will see the Z per unit is directly proportional to the MVA base, and the Z per unit is inversely proportional to the KV square. So we can see here the MVA base is the power is directly proportional to the impedance, per unit impedance, and the per unit impedance is inversely proportional to the kV square. So based on this concept, we are going to change. So if you have to change the given old base, so we need to see that is the old base, and I need to see the given impedance on the new base. Then we have to change how the values is changing according to the MVA base and KVA base. So Z per unit new is equal Z per unit old into, according to this one, we have seen that Z per unit is inversely proportional to KV square. So the new base by old base, then the MVA base is directly proportional to the Z per unit. Then you can go for the new base by old base. By using these formulas, we can calculate the change in base values. So we'll see the some of the problems. So first we'll consider here the exercise 1. A 3.3 kV 5 MVA single phase generator had source impedance ZS of 1.2 ohms. So on base values 3.3 kV and the 5 MVA of single generator, the value is given is the 1.2 ohms. Now determine the per unit voltage, per unit, the given source impedance in the per unit as well as percentage. So first we will see the base values is given 3.3 kV and the base MVA is 5. Then by using the formula, Z per unit is equal Z per unit in ohms, the source impedance in ohms into MVA base by KV base square. So then we'll get the 0.05 per unit. Then the whatever the per unit value came, you just multiply by the 100, you'll get the percentage value. So similarly, you can go for the exercise 2. We'll pause the video and solve the exercise 2. Then similarly, exercise 3 and the exercise 4. Okay, these are the very important and the very confusing part. Exercise 3 and exercise 4. First, we will see the exercise 3 here. 30 MVA 11 kV 3-phase synchronous generator has an impedance of 3 ohms. Okay, the values are given in the ohms. Determine the per unit value of impedance at 100 MVA 22 kV. So by seeing these two base values, we will confuse here. Now I can use the change in base formula to calculate the given impedance in the per unit, but it is wrong. The value you will see here, the given value impedance in the ohms. So we need to consider these base values. So directly go and calculate on the given new base values. So I can say here that we need to determine the given impedance on the 100 MVA 22 kV. So directly use the simple formula. So Z per unit is equal given impedance value in the ohms into MVA base by KV base square. So 3 into 100 into 10 to the power 6 by 22 into 10 to the power 3 into whole square. You will give the base, the per unit impedance on the 100 MVA 22 kV. This is the very important. First we need to see that the parameter, the given parameter which is in the per unit or three phase per unit or ohms. Then we'll discuss the exercise 5. Now we'll see here the a 50 MVA 11 kV 3-phase synchronous generator has an impedance of 1.2 per unit. Now we'll see the given impedance in the per unit. Then calculate the impedance on per unit on 150 MVA 15 kV. So now we can see here. So the per unit value is given in the old base values. So we need to convert into the new base value. So now use the change in formula. So 1.2 is given the per unit into the old by new. Here the new voltage is inversely proportional to the given per unit impedance, and the new base is directly proportional to the given per unit impedance. So from there you can see here you'll get the old by new, the new by old. Okay, it is in the base MVA and this is the KV. So then we'll get the new impedance on the new impedance in per unit on the 150 MVA 15 kV. So like that you can solve all the represented problems which you are considering by given parameter which you have to see the whether given the impedance in the ohms or per unit. So and then we'll see they are asking to convert in the different base values, or they are asking for the impedance in the per unit or impedance in the ohms. So this is the simple problem. So we can work here the per unit representation of the transformer by using the concept of referred to parameters. So ultimately at the conclusion we will come here the representation of the impedance in per unit of the primary and the representation of the impedance in per unit of the secondary both are same. Okay, so you can give the conclusion here. Z primary in per unit is equal to Z secondary in per unit, both are same. At the conclusion we will come here, Z primary in per unit is equal to Z primary in Z secondary in the per unit of the transformer, both are same when we are converting into the per unit system. So here a 50 MVA 132 kV by 33 kV 3-phase power transformer has an impedance of 12 ohms. So you will see here the given value in the ohms and per phase on the HV side. So value is given at the HV side. Determine the per unit value of impedance on the LV side at 125 MVA and the 50 kV. First, we need to convert the given impedance value in the ohms to the per unit. Okay, the value is given where in the HV side. So 12 into 50 by 132. We will give the per unit impedance on the HV sides. Now, according to our per unit system, the impedance on the primary side and the impedance on the secondary side in per unit of the transformer both are same. So by considering that, we will calculate the given new base value. The value is given in the after converting the the impedance value in the per unit. Now the value is given in the old base value, so we need to convert to the new base value. So by using the change in formula, then you can calculate the per unit impedance on the LV side on the new base 125 MVA 50 kV. You can calculate. This is the very important. Here we need to see the concept of per unit of the transformer. So similarly, you can try pause the video and try this here. The value is given in the impedance R plus JX, and you will try to convert to the per unit. The value is given in the per unit of the transformer. So we need to calculate the impedance in the ohms at the HV side. So HV side means here the 11 kV. We need to calculate. So pause the video and solve this problem. So then we'll go for the load flow analysis. First we'll see what is the basics, what is the significance of doing the load flow analysis, or we can say the power flow studies. So power flow studies are of great importance in planning, designing the future expansion of the power system, as well as in determining the best operation or performance of the exiting power systems. The primary information get from the load flow studies are, we can see the voltage value, phase angle, real power, and the reactive power. These are the four quantities which we'll get by running the load flow studies of any particular power system. So we'll see the simple large interconnected power system which has the two generator. It is connected to the two transformer to the interconnected grid. So you can see here the interconnected grid. From there we can consider the any one bus. Okay. So this is the simple representation of the bus. From bus the incoming current is I, and the outgoing current to the different buses is connected. So I can consider here the V1, V2, V3, Vn all are the buses. So I'm from this bus, I represented the bus P. Okay, yet each bus we can see the complex power at the bus P. So for example, we will consider the bus P, the complex power at the bus P, SP is equal PP plus J into QP. So similarly, we can write here VP and IP conjugate. This is the complex formula, the complex power which will represent in the PP plus JQP, and we can go for the representation of this. Then VP is equal mod VP, the magnitude and the phase angle at that particular bus. Then we'll see the four quantities here: the real power, reactive power, voltage, and phase angle. So based on these four quantities, we will classify the different buses in the power system. Okay. In solving the power flow problem, the system is assumed to operate under balanced condition. So we will see here the load flow analysis when we consider, then the system we will assume has a balanced condition, and a single phase model will use it. So instead of representing the three phase, we can always use the single phase because we are considering the balanced condition. The four quantities are associated with each bus. So each bus has the four quantities. Those are voltage magnitude, phase angle, real power, and reactive power. So based on these four quantities, we are going to classify the three different types of buses. So one bus we can go for the voltage control bus. First we'll see the three major classification of the buses in the power system. So first bus we'll say the slack bus, swing bus, or reference bus. The specified value is voltage and the phase angle it will give, and the real and reactive power we don't know. We need to calculate the real and reactive power as the reference bus. Then we'll see the load bus. P and Q value are given, and the voltage and the phase angle we need to determine. And the generator bus or PV bus, P value and the V value is given, Q value and delta value we need to calculate from the load flow studies. Then this is the special case where we have to see that voltage controlled bus, P value, V value, and Q value is given, only the phase angle of the voltage is not given. And you will see thus the most of the buses in the power system, around the 85% of all buses in the power systems are the load buses, or we can say the PQ buses, and the only 15% of buses we can say the generator bus or the PV bus. So you will see the significance of the slack or swing or reference bus. So when you are doing the load flow analysis, so the each line has some power losses. Okay, we need to account for all the generator 1, generator 2, generator 3 is supplying the line losses in the power system. So instead of that, I need to consider here the only one generator is entirely supplying the losses at which are corresponding demand. So that bus we can consider as the slack bus or reference bus. Okay. So in order to simplify the loss calculations, we will see the significance of, we can discuss here the significance of slack bus. So each will represent the significance of slack bus. In order to simplify the loss calculations, the losses are supplied by one particular generator rather than distributing among all the generators. So okay, so here the meaning is, so we are considering the only one generator we supply the entire losses instead of distributing all the generators. Okay, the generator which will supply the losses along with load demand is referred as the slack or swing or reference bus. Okay, generally the larger rating of the generator which is considered the slack bus in the power system load flow studies is the very important, which you will see here. The generator, either 4 generator is given and there are the different ratings. Okay, 5 megawatt, 5 MVA, 6 MVA, 10 MVA, like that is they will give in the generator. So which we have to select that the larger rating of the generator we have to consider the slack bus. Then we'll divide, we'll see the mathematical expression for the load flow equations. So based on this load flow equation, we are going to run the load flow methods such as the Gauss-Seidel Newton-Raphson method and the fast decoupled method. So first, it is the simple bus representation in the power systems. So let's consider how the bus is indicated as the P. The value is the current passing through that bus is IP. From incoming current to output current, we can see here the voltage at the particular bus is VP. So here we can go for the magnitude of VP at an angle of delta P. So we can represent the each bus. Now apply the KCL at this point. So incoming current is equal to outgoing current. Okay. So in this current, we can see here the admittance into this particular voltage. This admittance into this particular voltage will give the current value of this line. This admittance into this voltage will give the particular value of the current passing through this line. Similarly, you can see here in the load, we can calculate the line value. So instead of this individually, we can go for summation of k is equal to 1 to n, and we can go to the ypk into Vk. So Vk means here k is equal, we can get the 1, 2, 3, then it will get the voltage buses of this bus, voltage of this bus, voltage of this bus, and voltage of other load flow, other buses or other loads in the simple representation of the bus. So here IP is equal summation of k is equal to 1 to n. So this value will indicate the current values. So admittance into voltage will give the current value. Similarly, you can see here the I is equal V by Z, or we can say the Y into V. So 1 by Z is equal admittance. So from here we can get the current value. So similarly, the complex power at the bus, we have seen already in the simple representation of the bus, SP is equal PP plus J into Q. So we can represent the VP into IP conjugate. If the P is equal to the 1, 2, 3, we can show the number of buses. Let SP conjugate. Now we are doing the conjugate of this. So SP conjugate is equal, we can conjugate to PP minus JQ. Then it will shift here the VP conjugate into IP conjugate. Okay, the conjugate will indicate the complex conjugate to indicate the negative values or the positive values of the reactive power. So it will indicate the reactive power consumption and injection in the power system. So SP conjugate is equal to PP minus JQ. So this expression 4 will come. From the expression 4, we can separate the real line imaginary parts, then you'll get the equation 5 and the equation 6. Now substitute the values in terms of the magnitudes and their phase angles. So VP is equal to mod VP into delta VP, and the VP conjugate is equal to VP into minus delta VP. VK is equal to mod VK into delta K, and the YPK is the admittance into their corresponding angles. Now we can separate the terms in the real and reactive power, then you will get the equation 7 and equation 8. So equation 7 and equation 8 we are considering as the static load flow equation in the power flow studies. So this is the mathematical expression there we are representing the equation 7 and equation 8 is the static load flow equations. So from the equation 2, we'll see here in the equation 2, the SP is equal to PP plus JQP or VP into IP conjugate. From there, we can get here the IP value is equal to PP minus JQ under divided by VP conjugate. From there, we'll get the current value of that particular bus. So incoming current into that particular bus. So we know that IP is equal to summation of K is equal to 1 to N and VK into YPK is equal this term. From there, you can get the value of YPP and VPP. From this YPP and VPP terms, we can get the VP. Now we are getting the incoming current to that particular bus P and the voltage at that particular bus VP. So this is the expression 9 which will use to calculate the voltage at particular bus. So for example, P is equal to 1, 2, 3, 4, 5 up to the n buses. So we can use this formula to calculate the voltage at that particular bus in terms of the real power, reactive power. So you can see here the real power, reactive power, voltage value and the impedance matrix. Now we can see the given impedance, values, the given line impedance. Now we will convert into the admittance matrix. Then we'll see here if this is the admittance matrix. YPP will indicate the self admittance of the bus P. Now we'll consider the approximated values, pass the value, and we'll see how we are going to consider in the approximated load flow equations. The only thing we have to consider here the R value and G value. So the real power losses in the line we are considering as a 0. Then we'll see the negative, the only power will consume the reactive power will always indicate the 90 degrees. From there we'll get the P value and Q value in terms of the approximated value. Now we'll see here the formulation of the nodal admittance matrix. So from the equation 9, we will see here we need to calculate the voltage value at each bus. The voltage value at each bus, first we need to compute the admittance matrix of that particular system. Okay, if we get the 2 bus system, 3 bus system, 4 bus system, 5 bus system, we need to first calculate or form the admittance matrix of that particular bus. Okay, so here the simple bus 2 bus system is given. Generator 1, generator 2 is connected to the transmission line, has the impedance Z12 and the shunt admittance, that is capacitance, we give the Y12 dash. Okay, so according to, we will see here whenever the capacitance is there the sending end side, we can divide it in, we can represent it in terms of the equivalent pi model, or we can say the equivalent pi model. So the given capacitance at the receiving end side is divided half of and framed at the both the sending end and receiving end. Okay, so y12 dash by 2 and y12 dash by 2 given here. Now the converted line impedance to the line admittance. Okay, so y12 is equal to 1 by z12 will give the line admittance. The current passing through the at bus 1 is I1, the current passing through the bus 2 is I2, and in between the 1 and 2 we'll say the current passing from the bus 1 to bus 2 is I12, the current passing through the bus 2 to bus 1 is the I21, and this is the impedance. The current passing through the ground, the I10, the current passing through the bus 2 to the ground is I20, I10 and the I20. This is the equivalent pi model of the given figure 1. So this is the figure 1, this is the simple 2-bus power system. It is represented in terms of the equivalent pi model. So from here, apply the KCL in the node 1. So from apply the KCL node at this point. So I1 is equal, incoming current is equal, outgoing current. I1 is equal I12 plus I10. From there, you'll get this equation. So calculate the I1 value. I1 is equal, so this I10 is equal 0 volt. So V1 minus 0 divided by this Y12 dash. So here, this is in the form of admittance. Then you can multiply with the voltage value, you'll get this current value. So similarly, you can see here the V1 minus 0 into Y1 dash by 2. This will give this I10, then V1 minus V2 into this Y12 will give this I12. So from there you can simplify and we'll get the equation 1. I1 is equal Y11 V1 plus Y12 V2. So here the capital Y11 is equal is the self admittance of the bus 1, and this is the Y12 is equal half diagonal elements of the transfer admittance between the bus 1 and bus 2. So similarly you can apply the KCL at this point, and I2 is equal I20 plus I21. So similarly you can frame this one. So here we need to consider here the line admittances are half diagonal element and the diagonal element. So this Y11 and the Y22 will indicate the self admittance, and the Y12 and Y21 is with the half diagonal elements, or we can say the transfer admittance. So Y12 is equal capital Y12, this is the half diagonal element, is always negative of line admittance. Remember this point when we are solving the problem, that time we will see the how we are going to consider these values. This is for the simple 2-bus system. Now consider for the simple the n-bus system. So I1, I2 up to the IN, and the V1, V2 up to the Vn. You can say here the up to Vn. Then Y11. So this particularly will show the self admittance of the particular buses, bus 1, bus 2, bus 3 up to Nn, and the remaining components, the remaining parameters in this bus will indicate the half diagonal elements. So now we see the I-bus, the size of the I-bus is n into 1. So number of n rows and the one column, n rows and one column. So n rows and n columns. So first we need to form the admittance matrix. First we'll see the number of buses. If n is equal 3, then size of the Y bus is 3 into 3. So size of the Y bus 3 into 3. First we need to see the how many parameters or how many quantities is there in the admittance matrix. The diagonal elements of the Y bus will always say the self admittance. The half diagonal elements of the Y bus gives the transfer admittances, and this is the very important point when the center element is connected to the exiting system. So existing system, you will connect any center element, then only diagonal element of the Y bus matrix will affect. When your series element is connected in the existing system, the diagonal as well as the half diagonal elements will affect in the Y bus matrix. So when you go and simplify the problems, when already we have calculated the admittance of this given simple bus system, then I will tell them we need to include the one shunt component at the bus 1. No need to go for the entire matrix calculations. So we will see that when you are connecting the shunt element, the only diagonal element of the bus is changed. Okay, when you go for the series element, both the diagonal as well as the half diagonal elements is going to change. So we'll see here the simple problem. So let us consider the 3-bus system, bus 1, bus 2, bus 3, and is given as their corresponding impedance, line impedance values Z12, Z13, and Z23. You can go for the Z23. So these are the line impedances, the given line impedances. Now convert the given line impedance into the line admittances. So Y12 is equal 1 by Z12, Y13 is equal 1 by Z13, the Y23 is equal 1 by Z23. So after converting the given line impedance to the line admittances, now represent in terms of the reactance diagram, or we can say the admittance diagrams, Y12, Y13, Y23. Okay, so after this getting the line admittances. Okay, so here we'll see here the self admittance of this particular bus 1. So we'll calculate here. We'll see from the bus 1 how many lines are terminating. So at the bus 1, the Y12 and Y13. So capital Y11, capital Y11 is equal. You can see here the Y12 and the Y13. It is with the self admittance of the bus 1. Similarly, you can see here at the bus 2, the how many lines are terminating. So Y12 and the Y23. It will give the self admittance of the bus 2. And similarly, you can see here the bus 3. So 2 lines are terminating Y13 and the Y23. So Y13 plus Y23 will give the self admittance of the bus 3. Now we can consider the half diagonal elements. There we can see the transfer admittances. So capital Y12 is equal minus of small y12. So we will consider here capital Y12 is equal small y12. So we will consider this value and we will represent in the admittance matrix. Okay, we can say the Y bus. If n is equal 3, then size of the bus is 3 into 3. The very important. We will see here. This concept we will use when we will calculate the Jacobian matrix size of the Jacobian matrix. So similarly, you can see here the MATLAB code. We will calculate the admittance matrix. So first we need to see the given line impedances between the bus 1 and bus 2, bus 1 and bus 3, bus 2 and bus 3. Now calculate the admittances. Calculate the line admittances. Y12, Y13, Y23, and we'll see the n number of buses is 3. Then the size of the bus is 3 into 3. Initialize 3. Then calculate the Y11 is equal this by using this formula. We'll calculate the self admittances by using these formulas. By using calculate the half diagonal elements, or we can say the transfer admittance of the bus 1 to bus 3, bus 1 to bus 2, bus 1 to bus 3, bus 2 to bus 3. So this is the simple by using the mathematical expressions, and this is the generalized formula which we are going to calculate the entire matrix by given in the form of table, or we can say the from bus to 2 bus R value and AX value. Then you will get the this exact matrix by forming in the MATLAB code. So similarly, you can try for this problem. Pause the video and try for this problem. So here the 4 bus systems are given: bus 1, bus 2, bus 3, bus 4, and we need to form the Y bus matrix. So n is equal to how much? 4 buses. So the size of the bus is the size of the Y bus matrix is 4 into 4, and this generator will indicate as the ground. So from this line, after converting the given line impedance to the line admittance, then you can draw the admittance diagram. So now you can see we need to calculate the self admittance of the bus 1. Now we see the terminating the number of lines terminating from the bus 1 is this one, and this one. Add these three, we'll get the this value. Like that, similarly at the bus 2, we'll see the terminating value, terminating line from the bus 2 is this value, and this value. Add this thing, we'll get the this value. Similarly at the bus 3, so this one, and this one. Add these three, we'll get the this self admittance of the bus 3. Similarly for the bus 4, the only one line is terminating from this, that is y minus j2. So we'll calculate the 4 into 4 matrix of the Y bus, because n is equal given as the 4 bus. So similarly, you can model for the code for the MATLAB. So first we'll go the step by step, which you are follow the mathematical expression to calculate. Then we'll go for the generalized formula to determine the Y bus matrix. So this is the generalized formula. There he is giving the S shunt. Then get the here. Now consider the line charging capacitance, or we can say the line charging admittance between the buses. Okay, for simplicity purpose, I have represented this bus, but actually it is in the this line. Okay, we can go and represent it like this, and this one is from not here, we can go and represent like this. So it will be here, and the this line will be the here. This capacitance value is here, and this capacitance value will be here. Okay, so we can go. I'm not getting the errors in here. Please let me check first. Okay. So, yeah, you can see here that this value is connected here, and this capacitance is connected here, and this capacitance is connected here, like that in the diagram. So from the line 1 to 2 has the line impedance, 1 to 3 has the line impedance, 2 to 3 has the line impedance, and between the 1 and 2 has the line charging admittance, 1 to 3 has the line charging admittance, 2 to 3 has the line charging admittance. So first step is we need to see the n number of buses. So how many buses are given? N is equal 3. Then size of the matrix is 3 into 3. Now convert the given line admittance to the given line impedance to the line admittance. Now here converting that, these are the given line impedances between the line 1 to 2, 1 to 3, and 2 to 3. Then convert from the line admittances y12, y13, y23. Now we'll see here, after modeling this, we'll draw the reactance diagram, or we can say the admittance diagram. So here, so for example, in the diagram, you'll see here the bus 1, bus 2, and see the bus 3. So in between these lines, it has the line charging capacitance, or from here to here, it has the line charging capacitance. From here to here, it has the line charging capacitance. So at each buses, we can divide to the half at this bus and half at this bus. The same concept which you follow here. So y12 dash at this bus, y12 dash at this bus. Okay. Then y13 dash. So y13 dash at this bus and y13 dash at this bus. So similarly y23 dash at this bus and y23 dash at this bus. Okay. So combination of this, combine this y13 dash by 2 plus y12 dash by 2 is equal y10, then y30, and y20. So similarly, you see there y10 we can go for the y12 dash divided by 2 plus y13 dash by 2, and y13 dash by 2 plus y23 dash by 2, the y13 dash by 2 plus y23 dash by 2, it will give the y10, y20, and y30. This is the simple admittance representation. So similarly, you can calculate the y10, y20, y30. Then you'll go for the self admittance of the y1, self admittance of bus 1, bus 2, bus 3, and once we calculate the self admittance, we go for the half diagonal elements of the transfer reactances. There you can see for the each buses we need to see the how many lines are terminating. So for example, calculate the self admittance of bus 1. So this bus 1, we will see the how many lines are terminating from the bus 1. So this line, this line, this one, and this one. So summation of all all four will give the admittance of self admittance of the bus 1. Similarly, at the bus 2, you'll see how many lines are terminating. So this one, this one, this one, this one. So summation of all four will give the self admittance of the bus 2. So similarly, at the bus 3, you can see for this bus, this line, and this line. Summation of this 4 will give the self admittance of the bus 3. So like that, we can go and verify the admittance matrix of the given bus system. Now we'll try here. So pause the video and try for this. So in the problem 1, you can see the calculate the admittance matrix by giving the simple line impedances. Now suddenly, after calculating the admittance matrix of this problem, now I add the series element between the 2 to 3. Now entire diagonal and abdominal matrix is going to change. So suddenly you can add the series element between the 2 to 3. Then you will see the line is added between the 2 to 3. It is given in the impedance. Now we can calculate the entire matrix, because when you connect the series element, the both abdominal matrix and the diagonal matrix is going to change. So now we'll see the nodal admittance matrix by considering the regulating transformers. So when you are considering the regulating transformer, we'll see the two cases, case 1 and case 2. So first, regulating transformer can be used to control the real and reactive power flows in the transmission line. Okay, by using the regulating transformer in the transmission line, we can control the real and reactive power as well as the voltage level of that particular line. Okay, from bus 1 to bus 2, we can say the sending and receiving the buses. So when you are considering the regulating transformer, first see the case 1, representative of the regulating transformer showing the admittance opposite to the tap changing. So here tap changing is A and the admittance is showing in the opposite direction. In the case 2, representation of the regulating transformer showing the admittance same side to the tap. Okay, tap is this side and the admittance showing in the same side. So first we will see the case 1. In the case 1, the tap changing is showing the opposite of the admittance. Now we'll see the P bus and the J bus, and in between the admittance, the line admittance is YT and the regulating transformer is given here, and which has a tap 1 is EA. Okay, the complex power at bus P is VP into IP conjugate. The complex power at the VJ is VJ into IJ conjugate. Now SJ is equal, so SJ is equal to VJ into IJ conjugate. We'll see here. So by applying the transformation ratio, VJ by VP is equal to EA. So we'll see here the VJ by VP is equal to EA. So we need to get the VJ is equal in terms of the VP, A into VP. So in place of VJ, you can substitute this value. Okay, SP is equal, from here the complex power flowing from this side and the complex power flowing from this side. So we can say here SJ and the SP. So SP is opposite of SJ. So then we can represent as the SP is equal minus SJ. Okay, so VP IP conjugate is equal minus A VP into IJ conjugate. Like that you can represent here. Now you can, from these two values, so VP is cancelled. So IP conjugate is equal minus A into IJ conjugate. So now apply the conjugate on both sides, then you will get the VP I minus IA conjugate into IJ conjugate. Now here, instead of here applying the both sides of the conjugate, then we need to calculate the IP value. So IP is equal, from this diagram, IP is equal YT into VP minus VX up to this point. Okay, the drop will happen in here. So we need to calculate the IP value for this point. Okay, IP is equal YT into VP minus VX. So IP is equal YT into VP minus in place of VX. Now we can apply here VX by VP is equal to A. So otherwise for the transformer, you can say here, for the regulating transformer, Vj by Vx is equal to EA. So Vj by Vx is equal to EA. So in place of Vx, we can apply the 1 by A into Vj, 1 by A into Vj. Then IP is equal to YT into VP minus YT by A into Vj. We can get the equation 1. Similarly, Ij is equal to minus 1 by, so from here, from this expression, we can get this value. So Ij is equal minus 1 by A conjugate into IP. Now substitute the value of IP, then you'll get the expression of I2. Now represent the equation 1 and equation 2 in the matrix form. IP Ij is equal to YT minus YT by A minus YT by A conjugate YT by mod A square. Now here, when you are multiplying the A conjugate into A, we'll get the mod A. Okay, then this is the Y bus matrix of the transformer. Regulating transformer is given in the transmission line when the tap changing is opposite of the given admittance. Now represent in terms of the series element and shunt element by using the two-port network concept. Okay, so the given value is Ypj is equal minus Ypj. Okay, this is the capital Ypj is minus Ypj. So the minus Ypj means here the capital Ypj will go here, then it is the Yt by A. So this value is the Yt by A. Directly you can write. Now you can use the shunt element at the sending end side, shunt element at the receiving end side. So for that we can calculate that Yp0 is equal the self admittance of this bus minus that Ypj. Okay, so self admittance, this is the Ypp and the is this series line admittance Ypj. Then you will get the Yp0. Similarly, self admittance of this bus and the series element of the Yta. So we will get the this from here you can get. So here the yjp. So it is the ypj, then the ypjp. So similarly, you can get here the yt into 1 minus a by mod a square. If the tap changing is always real, then complex conjugate will doesn't matter to the tap changing. So similarly, so it is the equivalent circuit representation of the regulating transformer is given in the transmission line. Okay, the transmission line terminated between the bus P and J with the regulating transformer when the tap changing is opposite of the given admittance. Then you can go for the this is the equivalent circuit. Very important for solving the problem. Similarly, you can go for the representative of the regulating transformer showing the same side. The given admittance is the same side of the tap changing. Okay, so here you can see the tap changing is same side of the given admittance. Now apply the same mathematical expressions to calculate the admittance matrix. So first we will start with the complex power at the bus P is SP is equal to VP into IP conjugate. Similarly, at the VJ at the J bus will the SJ is equal to VJ into IJ. Now the power flowing from this side is the SJ. The power flowing from this side is the SP. Now apply here IP is equal to minus T conjugate into AJ. Okay, in place of T earlier we have seen the A. So by the confusion part I have divided I have shown in the two representation A and T. So similarly you can get here. Now get the IJ value. Now from this side you'll get the IJ value is equal to YT into VJ minus VX up to this point. Okay, from the current passing through this YT is give the VJ minus VX into YT. So here you'll get this value. Now IJ is equal to YT into VJ into we substitute here. So in place of here Vx by Vp. So from Vx by Vp will give the T value. Now this is the secondary side, this is the primary side. Vx by Vp will give the this T and the Vx is equal to T into Vp. So in place of Vx, you can substitute the T into Vp. Now we'll get the equation Ij, that is equation 1. Similarly, you can go for the Ip from this thing. Ip is equal. So this equation we can apply here. So Ip is equal to minus T conjugate into this value. We can substitute here. We'll get the equation 2. Now represent in terms of the matrix form. So Ip Ij in terms of the Vp and Vj will get the matrix here. Now calculate the series and shunt element by using the two-port network concept. Okay, so here we can directly go for the ypj is equal capital ypj is equal to minus ypj. So either minus ypj directly you can see here minus t conjugate into yt. So here ypj is equal to minus t1, but here the t is always real number, we can consider the direct t. Then yp0 is equal to ypp minus ypg. Okay, this is the self admittance of this bus and the series element the series line admittance of this bus. Okay, then it will give the yp0. Similarly, the self admittance of this bus j and the series element of the ypj y. Here we can say the yjp. This side, from this side we can see the yjp, and from this side to this side we can say the ypj. Then you will get the yj0. Okay, then we can represent it in terms of the equivalent circuit. Okay, so here the line is terminating to the regulating transformer when the tap changing is given in the same admittance side. Okay, this is the equivalent representation in terms of the pi model. So let's see the problem. We need to calculate the. So the line is given with the regulating transformer, and we'll see the condition. The tap changing is given opposite of the given line admittance. Okay, then we'll follow the equivalent circuit. So y23 divided by t. So when it is given, the tap changing is given opposite to the given line admittance. Then you can follow the equivalent circuit representation in terms of the pi model. Then we can replace here at the bus 2 and bus 3. Okay, the bus 3 is considered the P and the bus 2 is considered the J. Okay, then you can go for this representation, then calculate. Okay, first to see the given line impedances, then convert the line impedance to the line admittances. So here the line impedance from the 2 to 3 is given J 0.2, then you will convert the line admittances y23. Okay, so this y23 I'm making as the dash. Okay, to represent from the equivalent circuit y23 dash by t. Okay, so here we can see here the y23 dash is equal to y23 by t. So y23 is this given value. Okay, this given value in the impedance now is converted into the admittance. So similarly, you can calculate for the y30 and the y20. So y30 is equal to y23 into t minus 1 by t. So the tap changing value is given 8. Now you can use the t is equal to 0.8. By using this value, by calculate the equivalent circuit parameter first, then you can draw for the equivalent reactance diagram or equivalent admittance diagram. This is the equivalent admittance diagram which will show the all the values of the regulating transformer. This is the equivalent representation of the tap changing transformer which is given in the line. Okay, so after calculating you will get the Y bus matrix. So similarly you try for the one more problem here. So when the line is terminating with the regulating transformer but the tap changing is given same side of the impedance, then you can see the equivalent circuit representation of the regulating transformer when tap changing is given in the same side. Okay, so we'll try this different problem by using the combination of the regulating transformers and with the transmission line when the tap changing given in the opposite side of the given line impedance or admittance, and when the tap changing is given in the same side of the given line admittance.